The process of how text to image models work. These models are a fascinating application of artificial intelligence that transform textual dot descriptions into corresponding visual images. Text processing. All text-to-image models start by processing textual input. This involves converting the text into a form that the model can understand, typically known as text embeddings. These embeddings are high-dimensional representations of the text that capture its semantic meaning. Imagine a vast, multidimensional space where each point represents a unique piece of text. This is the world of text embeddings. At the center, there's a large glowing sphere representing the input text. The sphere is connected to multiple points in the space through beams of light, symbolizing the conversion of text into its high-dimensional representation. Each beam of light represents a dimension in the embedding space, capturing a different aspect of the text's semantic meaning. This image encapsulates the process of text processing in text-to-image models, where the input text is transformed into a form that the model can understand. Image generation. The core objective shared by all these models is to generate images that are visually representative of the input text. This involves creating an image from scratch or modifying an existing image based on the text description. The models learn to map the complex relationship between textual descriptions and visual elements. Visualize a large canvas, blank and ready to be filled. Above it, there's a cloud of words representing the input text. Each word in the cloud is connected to a paintbrush. The paintbrushes represent the models that are about to create or modify an image. As the words are processed, the paintbrushes start to move, painting strokes on the canvas. Each stroke represents a visual element derived from the text. The canvas gradually fills up, forming an image that is a visual representation of the input text. This image symbolizes the process of image generation in text-to-image models, where the models learn to map the complex relationship between textual descriptions and visual elements. Use of deep learning techniques. All these models leverage deep learning, a subset of machine learning. They utilize neural networks with varying architectures like GANs, VAEs, transformers, or autoregressive models, each designed to handle the intricacies of the text-to-image translation process. Imagine a vast interconnected web of neurons representing the deep learning models. Each node in this web is a neuron, and each connection represents the flow of information. Different sections of the web are highlighted, symbolizing the different architectures like GANs, VAEs, transformers, and autoregressive models. Each highlighted section is intricately designed, reflecting the complexity of the text-to-image translation process. In the background, there's a faint image of a brain symbolizing the inspiration behind these models, the human brain. These images encapsulate the use of deep learning techniques in text-to-image models, where complex neural networks are leveraged to translate textual descriptions into visual elements. Training process. These models are typically trained on large data sets of text-image pairs. The training process involves showing the model many examples so it can learn the relationship between text and corresponding images. The model's performance is evaluated based on how accurately it can generate images that match new text descriptions it hasn't seen before. 4. Picture a large library filled with books. Each book represents a text-image pair from the dataset. The books are open, and a beam of light connects the text on one page to an image on the other, symbolizing the relationship that the model is learning. In the center of the library, there's a table with a model, represented as a complex, glowing orb. The orb is absorbing the beams of light from the books, symbolizing the training process where the model learns from many examples. On the side, there's a closed book with a question mark on it, representing new text descriptions the model hasn't seen before. The orb is directing a beam of light towards this book, trying to generate an image on the blank page, symbolizing the evaluation of the model's performance. Loss functions. Although the specific loss functions may vary, they all aim to optimize the model's ability to generate relevant and realistic images. These functions measure the difference between the generated image and the expected outcome, guiding the model's training process. Imagine a balanced scale representing the loss function. On one side of the scale, there's a perfect detailed image, representing the expected outcome. On the other side, there's an abstract incomplete image, representing the generated image. The scale is not balanced, symbolizing the difference between the generated image and the expected outcome. Above the scale, there's a hand, representing the model, adjusting weights on the scale, trying to balance it. These weights represent the parameters of the model that are being optimized. In the background, there's a graph with a curve descending towards a low point, representing the minimization of the loss function during the training process. Please note that this is a conceptual description, and the actual process involves complex computations and algorithms. The image created based on this description would be an artistic interpretation of the role of loss functions in the training process of text-to-image models. Challenges and limitations. All models face common challenges such as dealing with ambiguous text descriptions, generating high-quality images, and ensuring that the generated images are diverse and unbiased. Evaluating the performance of text-to-image models can be hard, particularly because assessing the quality and relevance of generated images often involves a degree of subjectivity. Imagine a mountainous landscape representing the challenges and limitations faced by text-to-image models. Each peak represents a different challenge. One peak for dealing with ambiguous text descriptions, another for generating high-quality images, and yet another for ensuring diversity and unbiased images. On each peak, there's a figure representing a model trying to overcome the challenge. They are equipped with tools like a pickaxe or a rope, symbolizing the techniques used by the models to tackle these challenges. In the sky above, there's a cloud with a question mark, representing the subjective nature of evaluating the performance of these models. Beams of light are emanating from the cloud, falling on different parts of the landscape, symbolizing the varying interpretations of the quality and relevance of generated images. Historical overview. Early research in the field of automated image generation dates back to 2007. In 2015, neural networks could produce blurry images. As the generative neural networks became more sophisticated, the quality of the content they produced improved dramatically. It's been a journey of over 15 years, and the progress has been impressive. Meanwhile, there are a lot of roads ahead to improve, and how generative AI might play out in different domains is still subject to change. Text-to-image models, like the ones used in AI, do not pick up images from websites. Instead, they generate new images based on the text descriptions provided to them. These models are trained on large data sets of images and corresponding text descriptions, which allows them to learn how to create relevant images from text inputs. However, the generated images are entirely new creations and do not come from existing online sources. It's important to note that while these models are impressive, they are not perfect, and the images they create may not always be completely accurate representations of the text descriptions.